So before we get started, I would like to acknowledge the traditional custodians of the land on which Perth and Pawsey is located, and that's the Whadjuk people of the Noongar Nation. And I would like to pay respects to their elders past, present, and emerging, and extend that acknowledgement and respect to all First Nation peoples who are joining us today. Welcome. I'm Ann Buckhouse, Training and Education Manager at Pawsey, and we would like to welcome you all to the QuEra training and workshop that we have, a two-part session today and then again on April 2nd. Thank you, Pedro, for joining us. You are at QuEra's Computing Quantum Advocate, and you're a PhD in theoretical physics. Your research career throughout Brazil, the US, and Canada has explored topics in quantum matter and topological physics. Passionate about communicating quantum computing at all levels, which is great for us, thank you. Developing partnerships and helping users and developers alike understand ideal entry points in this technology. Welcome and thank you for leading this training with us. I don't know how you would like to handle questions. Would you like them in the chat or?
Always, as many as possible, and as interrupt me. I don't mind being interrupted. As Anne said, you're welcome to keep your videos on and off or off as preferred. I always encourage to keep the videos on because that tends to lead to more engagement, but of course you are not forced. We are going to have two sessions, and I think that they're going to be quite exciting. So the first day today, we're going to cover the basics of both the functionality of the technology and a little bit of our programming paradigm. So how to operate and deploy programs on our quantum computers. And on Monday, we are going to take a little bit of a different twist, and we are going to talk a little bit about the future. So we're not going to use crystal balls, but we are going to be talking a little bit about the upcoming technology, how this is developing, how it's changing. So you'll see a lot of differences between what we will talk about today and what we'll talk about on Monday. So without further ado, I will share my screen. I will encourage you once more to stop me at any time. And I think that we did share some materials with all of you ahead of time. So if you have notebooks and you want to follow with them, you're welcome to do that. Other than that, I feel like I just opened the wrong screen. So I will do this again. Ta-da! And oh no, I actually opened the right one. This is what you see, right? Pawsey 2024. All right, so we good. We have some. Yeah, Tuesday for you. You're right. The next chat is gonna be on Tuesday for you, Monday for me. If you have not received a link to materials, I will share a different link that contains roughly the same content right now.
That would be great, Pedro, because we did not share anything beforehand.
No problem. Not a big deal. Not a big deal. So here we go. So if you access that link, you end up on QuEra's GitHub repo for educational materials. What we are going to be covering is the content of roughly sessions 1 and 2, but we are going to do kind of compactified version of that just in a single day. And but the content is roughly the same as in there. There are notebooks, and soon we are going to be launching an educational platform where you're going to be able to access this much more easily. So stay tuned. Anyway, let's get to business because there's a lot of content. But keep pushing messages to the chat, and I'm pretty sure that Anne is going to continue sidekicking. And so I'll do Batman, you do Robin, and we'll do some polls and paths. So let's talk about the neutral atom, quantum computing with neutral atoms. Can I get a feeling, yes or no's on the chat? How many of you have had interaction with quantum computers? How many of you have heard of neutral atom quantum computers? just as to warm us up. So that hands up from Edric means yes, he did, or is that a question? It means yes, he did. Very well. Okay, have heard. So there are many ways of building quantum computers, and I guess the most famous one so far has been superconducting technologies. So you make little loops or almost full loops of superconducting material, and you use currents at a very low temperature to define your qubits, etc., etc., etc. Like if I call that Gen Zero, like the baby boomers of quantum computing or something, the next generation came with the ion traps, right? So ions, we always, I often get the question why we say neutral atoms. It's literally to make sure we distinguish neutral atom technologies from ions, because ions are atoms without their electrons. In our case, we're talking about atoms with their electrons. Everything neutral, everything just pristine as Mother Nature gave us. And yeah, if ions came as the, let's say, second quantum technology, I would say that neutral atoms can be thought of as the third generation. Of course, some people might argue about photons and photonics in the middle of the way. We don't need to. This is not a formal definition, right? So it's just so that we understand more or less how these technologies came one after the other and learn from each other for sure. Neutral atoms are pretty cool for making quantum computers because since they're neutral, you can pack them densely. They don't complain. They don't see each other. There's no Coulomb repulsion. There's, they just go. And that's pretty cool because we can make quite scalable systems, not only because we can pack a lot of atoms, which are going to be the base of our qubits, together, but also because the number of control lines. So one thing that we really solved, and this is going to be very clear on our chat on your Tuesday, is that this technology allows us to solve what we call the controls problem, right? So how many control channels do you have per qubit? Do you have more than one control channels per qubit, or do you have many qubits per control channel, which is actually what you're looking for? So we're going to get there. So efficient qubit control, but flexible problem encoding. So these guys holding ions are kind of convenient to hold because since they're charged, you can use electric fields and it's easy to access them. These fellas here, they have absolutely no charge. Okay, so the only way we figure out how to interact with them is to use laser light and to hold them in free space. So because these guys are living in free space, we can flexibly move them around and really find connectivities and play around with different ways of encoding problem. All of this together has been leading us to claim that this is the fastest path to error correction. And as we will discuss today, this also allows for new ways of thinking about quantum computing. Very well. So this is motivation. This is the why you should care about if you haven't heard, but looks like quite a few of you have heard. We are going to start with a very brief digression on what is quantum computing. So it seems like we get lots of experts, but let's just make sure that we are all aligned, in the same starting point. And the way I say that quantum computing works is that like any computing, you want to go from point A to point B. Point A is your information. Point B is the solution of a problem. And you have to transform that information that you know into information that at first you don't know, right? So we do that by information processing. So input is point A, result and output is point B. Usually you use bits, logical 0 1s to encode information. And you do logical gates, classical logical gates for transforming that information. And your point B is going to be a deterministic output. Now, quantum computing is not about computing faster. Quantum computing is about changing the rules, right? Quantum computing is like going from point A to point B, not with a Ferrari, but like through a tunnel instead of going uphill or something like that. If the problem allows, right? It's not every problem that you can have a good path between point A and point B by quantum computing, but just because you have new rules, you can envisage having new roads to get information across, right? So we use quantum bits. These guys live in a sphere, quantum logic, and the outcomes, they are going to be probabilistic. but in principle with well-determined probability distributions. With that understanding, I like to always mention that there are two paradigms for quantum information processing, and actually there's more. But for all our purposes today and for next week, we can just be thinking about two different operation modes for quantum computers. One we call analog, the other we call digital. Digital is what you have probably heard of before. It's sometimes people call just gate-based quantum computing. You take your logic, you decompose into a universal set of gates, and you're going to operate, if all these zeros are qubits in the beginning of your calculation, you're going to operate on them via 1 or 2 qubit gates and transform that information until you get to your result. Now, you have probably heard that these guys are noisy. So each of these operations introduce errors, and sometimes your Hadamards and X gates and whatnot, they don't transform your qubits as they are supposed to. So that's complicated. Now, analog operation mode for quantum computing is not so different. And what it is doing is to think of, instead of single qubit or 2 qubit gates and apply them discretely, you're thinking simply that the collection of transformations that you do on your qubits is going to be a unitary. So you don't care about single qubits or 2 qubit gates. You care about one big unitary that you're going to control as function of time, smoothly, continuously. And you can very well think of that as one many-body gate. That's it. Okay, that you control continuously in time. So these two modes, they have advantages and disadvantages. Today, we're going to talk mostly about analog computing. That's the machine we call Aquila, right? Our first quantum computer is accessible on AWS. And the advantage of working with analog computers is that because we don't break down the controls into several gates and sequential operations, but we have one single continuous operation, this is very robust to errors. And particularly when your target for quantum application is the simulation of a quantum system when the simulation of quantum system is your target for your application, this is very good. Okay, because the simulation of a quantum system is the simulation of the quantum dynamics, the time evolution of a system. And the only way of doing this with gate-based computing is by breaking that down into many, many small steps. Sometimes you hear the word trotterization, so trotterizing the process. And that's never going to be as efficient as simply evolving in time continuously, just regular time evolution. That's the best quantum algorithm that you can imagine for quantum dynamics. And I suspect that we will never find anything better than that, because by definition, that's what causes quantum dynamics, just unitary evolution. So this is pretty robust for studying quantum dynamics. It allows us to control several qubits with very few laser channels, as we would discuss, and entangle these guys quite easily at a quite large scale. Now, the hard part of this is that it's very hard to make one unitary that is absolutely universal and absolutely general. So it's going to be very hard for you to see an analog quantum computer that is universal. Okay, usually these machines, they are going to be able to coordinate a class of unitaries as function of time. And as long as that class is interesting and useful, all the better. You can definitely do lots of interesting things. And I guess my mission today is to convince you that with Aquila, there's plenty of things that are interesting to do and making this useful computer. So digital computing, as we will discuss on Tuesday, there's absolutely no reason to consider doing gate-based quantum computing without error correction. No way. Okay, and we will it's a strong statement. I will defend it on Tuesday. In the absence of error correction, I will claim that analog quantum computers are the next best option because of the efficiency of operations. So neutral atom quantum computers, and particularly analog neutral atom quantum computers, they operate in a way that we have been calling FPQAs. I don't know if many of you have a background in electrical engineering. If you do, or if you have heard of embedded systems, you hear of FPGAs, field programmable gate arrays. These are kind of programmable ASICs in some sense, so application-specific circuits that you can reprogram according to your application. We have been playing with the acronym here and calling these machines an FPQA, a field programmable qubit array, exactly because since our atoms, they live in free space, we can reprogram where they go. And contrary to the standard laptop that you have in front of you, probably, the chip or the processor doesn't come, it's not manufactured, right? You call, every time you talk to the computer, you create a new processor, you create a new chip, quote unquote, and you can create it in any way you want. That's why it's field programmable. You can program it, the qubit connectivity, in the way you want. One thing that you can do with it is to develop solutions that are pretty much problem dependent. So this is a classic example. I don't know if any of you has ever seen a map of Boston. If you haven't, this is Boston. This is actually Boston and Cambridge. So south of river is Boston, north of river is Cambridge, Somerville, and some other cities / neighborhood. And you could start thinking of, well, let's say you want to put coffee shops in Boston. There's many universities in Boston, so certainly coffee shops is a good business for you. Now, if you put too many coffee shops, let's say one in every corner, they will compete, right? You're gonna cover all your audience, let's say, or your customer base, but they will compete with each other because you don't want two coffee shops facing each other. Sometimes we feel like Starbucks doesn't think that. But so what do? You create a map of the city, you map the positions where you would like to put your coffee shop, let's say, and you mark it. And what we can do is to create a graph for every position of prime position to put your store or whatever it is, and create connectivities between them. If they're too close, they would compete. If they're far enough, they don't compete, let's say. And what we can do, because of this FPQA paradigm, is simply to do the same with atoms. So you don't need to work too hard on your creativity. This thing that you're seeing in the center is the same graph on the left, but made of atoms. Okay, so if you doubt it, probably you can see my cursor here, but you can look at this little motif on the bottom right, there's this little triangle, this little tree, and you can see, the little tree here, the triangle, and just trust me that if you go atom by atom, you made Boston in atoms. And by the way, each of these bright spots here is one single atom. So it's amazing that we can position them in any way we want. And well, these atoms, they interact if they're close, they don't interact if they are far. It's more or less the same story as in the left. So you can do a calculation. The atoms that disappear here, they're basically the answer to a question of where should I position my stars in a way that I cover all the space without letting them compete. So this is one thing that you can do with these machines. It's a classic example. No, it's not the only thing it can do, but definitely it's one thing that it does pretty well.
Excuse me, Pedro. With the
Yeah.
FPQA,
Mhm.
it's very interesting. I'm curious, how do you get the atoms to, how do you change the interaction with the atoms so you can reprogram them? From my knowledge, all I know is using like magnetic fields for quantum qubits.
Right. Thank you for the segue. Let's get to business then. So let's talk
Excellent.
about what's the architecture. So you don't necessarily need to know exactly the architecture of these quantum computers to be able to program them, but I encourage you to know it, okay? Because I think that you really need these analog machines. They operate really via heuristics, and heuristics for quantum many-body systems really require you to kind of have like a close relationship with the system so that you understand what it does and how it does. So let's figure out how we make these computers. And the way that I like to say is that we create these qubits via puffing up the atoms, and that's how we are going to generate interactions, to your point, Thomas. So we use rubidium. We don't need to use rubidium. There are other candidates. If you don't remember where is rubidium, here it's where it is. It's in the first column of your periodic table. First column, if we have chemists in the audience, you'll forgive me, but if you're in the first column, you're hydrogen, right? I don't care. It looks like hydrogen, quarks like hydrogen, has one electron in the valence shell like hydrogen. It's just heavier. The energy structure is actually different from hydrogen, but it feels very much like it. And the fact that you have a single electron in your valence shell allows you to control these systems fairly easily. And in particular, we are going to create a qubit. So if you remember, to make a qubit, you need 2 energy levels. I'll surprise you in the next week telling you that we are going to use 3 starting from next week. But today we're going to use 2. And these 2 are the ground state of rubidium, which is a 5s state, 5 being the principal quantum number, and 1 highly energetic state. Usually, if you have a highly energetic state of an atom, you call that a Rydberg atom or a Rydberg state. Okay, and the principal quantum number of the Rydberg state that we are using here is 7T, 70. Right, so remember that hydrogen, you start with this n equals 1. The smallest n possible in rubidium is 5 because of the occupation of the other shells with more electrons. We excite from 5 to 70. Okay, it's like super energetic. It's not ionized though. And one thing that is interesting about fun fact about physics is that when you puff up an atom, when the volume of a neutral body is proportional to the polarizability of that body, or vice versa. The polarizability of a body is proportional to the volume of the body. So if we puff it up, it becomes highly polarizable. Polarizable means that if I come with a charge, I can push a charge to one side, push a charge to the other side, create a little dipole, and then I can have interactions. So whenever we have an atom in the Rydberg state, it's going to be highly interactive. When it's in the ground state, it doesn't see anything. And that's the starting point. So what's the cycle of our quantum computer? What happens when you submit a job, right? You're going to think a problem, and you're going to figure out a geometry that you want. And what's going to happen is that your CPU is going to send a message to our quantum computer that is going to start loading what we call a MOT. We love our TLAs, our 3-letter acronyms. Okay, so MOT is the magneto-optical trap. It's a trap with optics and magnetic fields. It's a magneto-optical trap. Okay, so there's lasers, there's some magnetic coils, magnetic elements that generate some coils that generate a magnetic field, and this is capable of capturing a little cloud of rubidium with about like a few 100,000 atoms that's cooled down. And what we do then is the CPU is going to talk to a different element. It's called an SLM. We do like our 3-letter acronyms. The SLM is a spatial light modulator. It modulates light in space, right? So it's basically an active mirror that looks like it's a liquid crystal that you can program the voltages of every little piece of it. Think of it as a pixel, and that generates a phase shift in your light. So light comes with a single beam, but can reflect like the Fourier transform of whatever you put on that SLM. And that Fourier transform is going to be what you want. So let's say here, you wanted a square. You could want a penguin, you could want whatever you want. So as long as you can take the Fourier transform of a penguin, we can generate a penguin for you. And so the light that reflects from this SLM is going to pierce that cloud, and atoms are going to start loading on that light. So loading because of what? Because laser is not like lightsaber, right? Lightsaber is straight. You might see Star Wars, right? Star Wars. It's straight. But actual light has a little waist. We call it the focal point. And the focal point of light is actually sticky. Or there's a gradient in intensity that makes it sticky. Some biologists use it to hold cells. We use it to hold rubidium atoms. So this laser is passing through that cloud. Those atoms are already slow. So when they hit a little laser beam, they get stuck there. And that's what you're seeing here. So what you're seeing is a bunch of atoms getting stuck stochastically, about 60% of them go in the right place, and 40% don't go in the right place. So what do? Well, we create extra regions here. So that's what you're seeing, these extra rectangles on the sides. We're going to image the loading, this is stochastic loading. We're going to see where atoms are missing. We're going to see where they are not. There's going to be some processing to figure out how to best reposition these extra atoms in the extra regions in the right place, and now we're going to come with extra lasers that are movable, that are mobile, right? And these lasers, they are going to touch the extra atoms on the sides, and they're going to slide them into place. And this process we call sorting. So that turns 60% loading fidelity into a 99.9% loading fidelity. The movable, by the way, the moving elements that allow you to move lasers, they're called AODs. It's another three-letter acronym. It's the acousto-optical deflector. It deflects optics by acoustic signals. Anyway, so you sorted the atoms into place. I'm being very honest here and showing you even a case where there are errors. So yes, when you submit a job to our quantum computer, you might have to discard some of the runs, but usually you're gonna have to build quantum statistics anyway. You're gonna run like 500 times for every program that you have. So discarding 2 or 3 is not gonna really impact your results. That being said, we image again. Everything's right. Everything's in place. Good, great. Calculation happens. We shine some extra lasers. We're gonna get to what those lasers do. And that's going to do a calculation. It's going to send some atoms to the Rydberg state, others to the ground. You do that in a way that solves your problem. And in the end, what you get is going to be an image of this register of zeros and ones, where ones are atoms in the ground state and zeros are atoms that went to the Rydberg state. Okay, so you don't receive these images. I think it's easy for you. You just receive like a bunch of vectors with bit strings, 0, 1, 1, 0, and that's the answer of going to be the answer of your calculation. Are we okay with this? We're about to get some exciting stuff, okay? Because so now is the time. No questions? Okay.
Not so far in the chat.
All right. So let's play. Maybe you have heard of, you can think of gates. We can talk about a little bit of gates. Like if I say a 2-pi gate, right? I have a qubit pointing up. I apply a 2-pi gate in the x direction. This is going to rotate and come back up. Okay. I'm about to show you the computer actually working. You don't have access to these images. This is something that, exclusive when you talk to us, and we can show you what the images look like. So we're putting these atoms all far from each other. They don't see themselves. So there's nothing, they don't touch, they don't talk. There's no entanglement going to happen anyway. On the left, you see the stochastically loaded tweezers. In the middle, you see the sorted tweezers. So you can see that the user here wanted a nice square. And you can kind of get a feeling between the left and the right and the middle one that these atoms were very close on the left and they're pretty far apart in the middle, right? So for now, let's just use our intuition and to say, okay, far apart, they are not interacting. And on the right, it's post a 2-pi pulse. So we are taking a qubit, applying 2x gates if you want. Right, it goes from up to down, down, back to up. So North Pole is going to be shiny, South Pole is going to be dark. And you would expect all qubits to go back to where they were because it's a 2-pi pulse. But you're seeing that some of these guys here, they are blinking, they're disappearing. And that's basically noise. That's errors in your calculation happening. So if you never saw what errors in your quantum computer really look like, here's a very visual way of seeing that. And this is pretty cool because since I can make many qubits all side by side and not talking to each other, I'm automatically parallelizing. I would need to be running this many times if I had a single qubit for you to be the statistics, but here I can do for a bunch of them all at once. Thanks, Jess. Indeed, it is cool. So that was on me. The next one is on you. So I'm gonna run this and I'm applying another pulse. And if you have had experience with this, with quantum computing before, and you're comfortable with the topic, Can you give a guess of, like, I'm applying a pulse, it's perpendicular to z. Just tell me a fraction of pi, or a fraction of 2 pi, or a multiple of 2 pi, for that matter. What kind of gate do you think is being applied to these qubits? Feel free to paste in the chat or... H, somebody's pulling a Hadamard gate. Any other question? Any other alternative? Give it once. Give it twice. Why? No, I didn't say it was not a Hadamard gate. Actually, if you guessed a Hadamard gate, you guessed very well. A Hadamard gate is a pi over 2, actually. Yes. So this is a pulse that is sending you from the North Pole to the equator. And when your qubit is pointing in the equator, you may remember that it's going to have 50% chance of being measured up, bright, and 50% chance of being measured down. This is the good old up plus down over square root of 2. If you ever thought of what, whenever you write up plus down divided by square root of 2 on your notebook, if you want to think of what it looks in real life, here's what that looks like. Okay, 50% of the atoms are blinking, 50%-ish of the atoms are not blinking. I think that this is amazing. Okay, I every time I look at this, I get goosebumps because you are seeing like the quantum measurement and quantum operations. It's very visual, and that's what we are going to be playing with. Okay, the only difference is that we cannot do this individually in different ways. If I wanted to do a pi pulse or a 2 pi pulse in different atoms here, we would have a hard time because, as we will discuss, the lasers, they are going to shine on all atoms at once. Do we have any questions about the functionality of the machine? Because now we're going to enter the programming part. We okay?
Yeah. Might be, don't know how appropriate it is at this point, but how would we implement something like an ancilla register in an algorithm? So used to thinking in terms of digital quantum computers, right? Where if I want to sub-process, right, I just say, here's an ancilla register, which I'm using to prepare some bit of information. What does that look like in this?
You don't really. I mean, let me rephrase this, right? It is possible to have ancilla atoms that are going to affect the dynamics of your system in non-trivial ways, although you don't want them to participate directly. Okay, you can use ancilla atoms to pin phases, so you have a pattern that you're looking for. You can add an extra atom exactly in a place that you would have some degeneracy, for example. You add an extra atom in a given place that makes your degeneracy break, and you open and you get one pattern instead of another. There are some things that you can do where you place extra qubits in order to influence your calculation without you having to actually make them direct part of the calculation. But the way that you think about it is slightly different. Does that make sense?
I also suppose, I think that does. And I suppose since we're kind of cutting straight to the sort of Hamiltonian, the hope would be that you don't need a bunch of ancilla qubits because...
Exactly. Exactly.
Thanks.
So no problems. Let's see Lorenzo's question. The atom positioning is an optimization problem. In the example, we had the constraint not to interact with each other. Then for different problems, we need to implement different constraints. That's very much the mindset. So we are going to see just now that there are two ways of programming or two ways of thinking about programming these machines. Way number one is the time-dependent parameters. The second one is the geometry. So the geometry goes into it. Okay, and these computers, they don't come with a brick wall shape. It doesn't come with a square topology. It will look like whatever you need it to look like. So thinking of clever geometries is very much part of the programming paradigm. Let's jump to it then. So this is a little mock of the neutral atom quantum processor. We're putting, I don't know, that day I was thinking of honeycomb lattices, so I decided to put them in a honeycomb lattice. It's just an example. So every blue dot here is gonna be one atom, and what you see is some like this red motifs here. They would be the laser beams that are holding the atoms in place. The large blue, green spheres are the atoms that got excited to this Rydberg state. And the green field behind all of this, or on top of all of this, is a laser, is a large laser beam that is shining on top of the whole register. Technically, the secret is that there's more than one laser. It's more like it's like two lasers, and then each transition is actually a 2-photon transition, so it's actually 4 lasers. But the generally speaking, actually it's I think it's 2 lasers because they're just counter-propagating, but it is a 2-photon transition. But the point is that these lasers, they are shining over all atoms. Okay, so this is shining. These atoms, they lie in a plane. Before someone asks, I always get this question: no, you cannot do 3D, and no one will ever do 3D because we are gonna go from plane to dynamically reconfiguring. So you go from 2D to as many dimensions as you want, basically. So there's no need to think about doing 3D. So as far as the analog system goes, 2D is what we are gonna get. And you have this laser, so it's actually a large laser beam that's shining over the whole plane. Every atom is gonna get the same influence of that green laser field. And as we discussed in the beginning, computing is transforming information. Transforming information is time evolution. So even though you might be used to thinking of applying logic gates, the mindset here is that all that you want to do is to solve the Schrödinger equation. And to solve the Schrödinger equation, all you need to do here is to fix a geometry, fix the time-dependent parameters, and play with this Hamiltonian. So the Hamiltonian is the functional operator that is going to control the time evolution, right? So generally speaking, we just think of it as a matrix dimension 2 to the n by 2 to the n, where n is the number of atoms or qubits that you're gonna have. That's the hard part of doing in a classical system, right? The 2 to the n by 2 to the n can get very large. What's the Hamiltonian? Here's the math part. It was gonna arrive sooner or later, right? So hopefully we are not against math. I'm definitely not against math. So this is the Hamiltonian. I'm keeping the drawing on the bottom left here so that we all remember what's happening. But you have everything that you see here that has of t, function of time, you have control over as function of time, right? So omega of t, phi of t, delta of t. Notice that phi, omega, and delta do not have an index I or j. So they are the same to all atoms. We're installing some features that are going to allow delta to have some site dependence, but the other terms are definitely going to remain kind of global, okay, uniform to the system. Omega, let's talk a little bit about jargon. We call it Rabi amplitude because it generates Rabi oscillations. Phi, we call a phase because it's a phase. It's e to the I, phi, that I is not the label, the index I. That I is just the complex I refuse to call it j. And that's just the complex I. So phi is just a phase. You have control over that. Delta, we call it a detuning, right? So you can see what delta is doing down here in this diagram, right? It's changing the resonance energy between the ground and Rydberg state. And that leads to for your system to be out of tune, right? It's out of resonance, so that leads to a detuning. That's why we call it a detuning. De facto, you should remember that just omega controls terms that are off diagonal, and that leads to mixing. So it's like X gates, if you want. Phi just rotates the axis for that. So if you just have a pure omega, that's going to be on X. With a phi, you have a mix between X and Y. N, or delta, sorry, delta multiplies N, and N is going to be 0 in the ground state and 1 in the Rydberg state. So delta is a diagonal piece in this computational basis, ground Rydberg, and it's gonna give you a cost of 0 in the ground state and of delta when you have an atom that is excited. Now, all of this would be very, very boring because there will be no entanglement and no complicated dynamics and no nothing if it was not for an interaction term. And the interaction term is the last term. So this is the only two-body term that you see on this Hamiltonian. It controls the interaction between a qubit I and a qubit J. It has a coefficient Vij that is not a function of time. So you do not get to control it as function of time. Once it's fixed, it's fixed. But you do get to control it because it depends on the geometry of the problem. Vij falls with the distance between the two qubits to power 6. And therefore, if you put two qubits close, Vij is large. If you put two qubits far, Vij is small, with a very large power law decay. If you think a little bit and massage this a little bit, this is like an Ising model in the presence of a transversal and a longitudinal field, okay? But that's jargon. Might help some of you. Questions about this? This is where things start to get complicated, okay? Omega generates dynamics, delta generates energetic costs, and Vij is going to generate interactions. So to Vivek's question, Vij, the physical meaning is an interaction. It's a dipole, technically a van der Waals interaction. So between two neutral bodies, they have this van der Waals type of interaction. So it's a kind of a mutual polarizability. It's a second order process in perturbation theory. That's a dipole falls with 1 over distance to power cube. If you do that to second order, you get to 1 over distance to power 6 because it's 2 times. And that's the van der Waals interaction. So that's the physical meaning of Vij, or the physical origin of Vij. It's a van der Waals interaction. We good? More questions? What kind of constraints are there on the term Vij? Let's talk about that, right? So the constraints that appear on Vij, they are constraints on the geometry that we can deploy on the system, right? Clearly, this is a very physical system that we have in our hands, and there are going to be things that you can do and things that you cannot do. So let's talk about that. Good segue. Let me just check the time. Okay, we got time. We got like 30, 45 minutes. Is that right?
We actually have an hour and 15 minutes left, but if you'd like a break in the middle.
No, that's all good. We can keep talking. Worst case, we end early. I think that's not necessarily the worst case. So let's talk a little bit of the hardware constraints and the geometry here. And we are going to go from here, from this straight to a little bit of programming, and we can do that together. So you can see how we actually play with this. So let's say I have 9 atoms. Okay, I'm gonna put 9 atoms in free space. Of course, you cannot do whatever you want with them, as we were just saying, right? So Vij is going to change depending on how you position them, and there's gonna be limits. Like probably you cannot put 2 atoms on top of each other, just guessing, right? Wild guess, right? And probably you cannot put them 10 meters apart from each other because our system is smaller than 10 meters. So certainly there's gonna be some constraints there, and let's go through them. So first point is there's always a little positioning error of about 0.1 microns. And by the way, full disclaimer, this is going to be the only programming language that you're going to program with units, okay? So you're programming micrometers and you're programming megahertz, or technically radians per microsecond. So don't forget there's going to be units. So whenever we define the numbers in the program, those numbers, they correspond to quantities with units, okay? So positioning error, 0.1 microns. You have a play field. That play field is of size 75 microns in the x direction to 76 microns in the Y direction. No, there's not a typo. It is 76 microns in the Y direction. It's a very, very subtle suggestion to you that if you want to put things in an elongated direction, you should favor the Y direction. And you should favor the Y direction because de facto, the laser, that green laser, is actually coming from below here. And if you put things along the direction of the beam, the responses are going to be more robust. Okay, so you get usually better results if you do that. No, let h bar equals 1. Well, how was my previous slide here? Yeah, well, I actually set h bar to 1. but you yeah, well, sorry about that. I sorry, not sorry, right? So anyway, as I was saying, you cannot put atoms on top of each other. The laser beams would kind of not be distinguishable. You end up getting conflicts. And by the way, let's take a moment to appreciate that nature never wants us to build a quantum computer, but sometimes it actually does. If the loading of those laser tweezers, the stochastic loading, sometimes loaded 1, sometimes loaded 2, sometimes loaded 3, sometimes loaded 4, we would never be able to create a sorted system. The only reason why this works is because it's 0 or 1. If there are 2 atoms in the same laser, they collide, fly away. Both of them fly away. So it's 0 or 1. And so it's a moment to appreciate Mother Nature. But other than that, there is a minimal distance of 4 micrometers. Okay, so you cannot put atoms closer than 4 micrometers. When you're doing simulations on your laptop, no problem. When you ask for a job sent to Aquila, yes, problem. There is a non-trivial one here, that the atoms, you can position them in any order. As long as you're looking at the x direction, you can slide them continuously. But once you position one atom in a given y coordinate, the next atom along y has to fall 4 micrometers high away. That's a little convoluted way of explaining this. The short way of explaining this is that we sort in rows. So you cannot put atoms that are like too close to each other along the y direction, because remember that sorting process that I was mentioning to you, that happens in rows, and there will be collisions. We are actually relaxing this. There's going to be some smart sorting that we're doing that is going to allow this to go to 2 microns. But right now, for like general users, you have access to 4 micrometers and rows, always in rows. Does this make sense? Let me make an example for you. Okay, let's say I put an atom here, and then I put another atom here, and these atoms, they are gonna be 4 micrometers, right? But the next the best example for this is hexagonal lattice, actually, right? So imagine this, right? Like if I position one atom here and another atom there and another atom there, let's squish this in a 2D plane. The distance between this guy and that guy in the y direction, so in the direction that is always along this kind of looking diagonal, because I was unkind and made this perspective. So that the y coordinate is always constant. Okay, the distance between this guy and that guy along y, along this direction here, is the same as the distance between this guy and that guy. Now, if you go in this direction, in the x direction, the distance between these two guys, let's call it A. Now, the distance between this guy and the next row, you see that there's a little zigzag coming on here. So this distance here is smaller than this A, right? Because of the little angle. And if this distance is 4, this distance cannot be smaller than 4, because 4 is the smallest distance between rows. So this means that technically, if you sort with the y direction, right, along this plane, you're in bad trouble, because this distance of the edge of a hexagon is going to have to be much larger than 4 microns. But if you sort these guys with with y in this kind of diagonal-ish direction here, then the distance between this row and the other row and all the rows can be 4 microns because they are all uniformly 4 microns. So this is a little bit of a non-trivial geometry aspect to it. I can guarantee to you that the moment you start creating lattice, you start suffering through this. So right now it may sound a little abstract. How big are the atoms? Is the 4 micrometers between the center of them or the edge? It's an atom, right? It doesn't really have a size, right? So the typical size of an atom is order angstroms. When we excite it to the Rydberg state, it grows between 100 and 1,000 times, so it becomes kind of micrometer size. But it's actually much smaller than what you're seeing here. Okay, it's like 0.1-ish micron. So this distance, I'm exaggerating here. Okay, there's no edge of the atoms for you to consider. There's edges of the power law decay of the interaction. That's something that you do have to worry about sometimes. Let me jump to our little my little tutorial here, the notebook, just so that you see how this actually plays in your hands. So we have a program. It's kind of an SDK and a simulator. We call it Blockade with a Q and no U, because yes, right? So that's the program that we are generally going to be using to program Aquila. Blockade comes in 2 versions. It comes in a Julia version, nice, efficient, fast, love it. There's a Python version, boo, but it's actually very good for talking to the actual quantum computer. It's a little bit less efficient numerically, but for submitting jobs and batching and stuff like that, it's actually pretty good. So you use them at your own discretion. We're gonna cover mostly the Python version, and Blockade is pretty straightforward, I gotta say. So my colleagues, they really helped make this a straightforward thing to program. So let's say you want to put atoms in a given space. Well, you're gonna come to Blockade. You're gonna call this little method list of locations, and you're gonna feed it an array of tuples, and the tuples are gonna be the x and y coordinates of your atoms. Okay, so we can just run this and create here already a register that's gonna have 1, 2, 3, 4, 5, 6 atoms. These numbers, I emphasize, are measured in micrometers. 0 is 0 micrometer, right? 0.5 is 0 micrometers in x, 5 micrometers in y. So mind that. You can dot, so this is our atom coordinates. You can just dot show, and my friends made a little bookie widget here so that it can plot for you right away. You know, if you hit your head or forgot what you did, or you simply cannot visualize properly what you're testing, just dot show, you will see if you created exactly the array that you wanted to create. And you can hover your mouse and see which atom is which, 0, 1, 2, etc. What are their positions, and that should help it make it very easy for you